Hey everyone, thanks for joining us. Today's conversation is going to focus on gravity, the most pervasive force in the universe, the force that shapes stars and galaxies, gives rise to the expansion of the universe, gives rise to understandings of cosmology and so forth. And as most of the audience for the series of discussions that we've had over the course of months and years really is at least partly familiar. It's Einstein's general theory of relativity that gives us our most refined description of the force of gravity. But some lingering questions about gravity have been with us really for decades, which has to do with whether gravity should be thought of as a fundamental force in the universe, or rather, perhaps it should be thought of as a kind of secondary characteristic that emerges within certain contexts, certain environments. And from that point of view, maybe gravity is not as fundamental as we thought, not from the standpoint of its fundamental influence, but rather on its ontological status, like where it fits in to the fundamental architecture of the forces of the universe. And here to talk to us about these ideas is someone who I have known, I guess, for 40 plus years, if I can do my arithmetic correctly. It's Erik Verlinde, who's had a profound impact on our understanding of fundamental physics and on the development of cutting edge theories, going back to work in string theory and now pushing the frontiers of ideas that have to do with holographic ideas that we've discussed from time to time, and his own proposal of emergent gravity. So it gives me great pleasure to bring Erik Verlinde into the conversation. He's a professor at the Institute for Theoretical Physics in Amsterdam and really has been, as I mentioned, a driving force in so many of the key developments in physics over the past 40 years. So Erik, great to see you. Thanks for joining us.
Thank you. Great to see you too. I'm very happy that we can discuss these exciting ideas and developments in our field. And also good to see
Absolutely.
you indeed and talk about even the old days of string theory and what we did together in those early days of that.
Absolutely. And so just to give us a sense, are you in your office in Amsterdam now? Are you?
I'm in Amsterdam now, not in my own office, but close to it. I mean, this is what we call the theory lounge. So it's a room which we use for discussions and so on. And it's a nice location to do this interview.
Absolutely. So let's just jump right in. I mean, we're more or less, I think, the same age, within a year or two at most. So we both kind of grew up with the excitement of the initial developments in string theory in the 1980s. I don't know that we've ever discussed those years, and I don't want to dwell upon it too much, but what was it like for you in the 80s? Was there a sense that we were on the verge of the final theory?
Well, I was very excited to even start at that moment when these new discoveries came that we, well, knew how to go beyond, the standard model and that there was this new idea of using vibrating strings to describe forces of nature and all the sort of miracles that came out that we suddenly had a finite theory where things could be calculated and that we could be learning things about gravity together with the other forces. I was very excited about that, but I think I already at that time realized that we had something that was going to take a lot of time to really understand what it meant and how to use it in describing our universe. I mean, there was first the idea of trying to connect it, merely make predictions, say, for all the particles that we see in nature, like the standard model and so on. Turned out that was maybe a bit too well difficult. But what I found most exciting about it is its connection with gravity and that we can have finally a quantum description of the gravitational force and of space and time itself. I mean, this is where I had my own interests mostly. And I remember that as an exciting time to work in, indeed.
And so your fellow country person or countryman, I don't know what language is allowed these days, Gerard 't Hooft, of course, who was a future Nobel laureate back in those days, he famously was somewhat skeptical, if that's a good description of these developments. Did his perspective have an impact on the young Erik Verlinde?
Yes, I certainly it had. I mean, he was, of course, very influential already in that time with all the things he had done for the standard model, and he started already thinking about black holes and so on. And he had certain arguments why he didn't sort of like what we did in string theory with all these excited states, extra dimensions, and so on. But I felt like that string theory was so much sort of promising that I wanted to work on that, and he allowed me to do this. But I did listen to his arguments about he was already thinking about the paradoxes that came from the discoveries of Hawking about black holes and so on. And so even after doing my PhD with my brother Herman and with other yeah, young theorists like Robert Dijkgraaf and Karl-Jan Schoutens, we went to the institute in Princeton, and then there was one year where we said, well, maybe we have to also look at what Gerard Hooft was doing, because I did always follow what his ideas were. I read his papers, and I did think that his arguments were very clever. And so already at that time, I felt that there must be some way of combining what people learn about black holes and what we were doing in string theory to make further progress.
And so I'd love to come back to the details of that in just a moment. But before we get there, I'm wondering if you could share your reaction to something that I know, no doubt you experience perhaps at least as much as I do, but I get a lot of it. There's so much chatter today that string theory has failed, that this is a dead end, waste of time theory that somehow has not worked. My reaction to that, you can probably guess, is not to hype string theory and say it's the answer to every question that anyone has ever put forward, but to tout the incredible advances that have come from the theory and to note that it's a stepping stone en route to a deeper understanding. How do you respond when people say things like that?
Yeah, very similar as you do. I mean, I actually maybe even have to go back a little bit even before we entered string theory. I mean, I looked as a high school student to a program where Gerard Hooft was explaining the things he discovered about the standard model. And the second part of the program was about black holes, where also Hawking was well featured and what his ideas about what well Hawking radiation and all that. And now I feel very fortunate to have worked in that field and seen how much progress we have made. I mean, I think this is really because that's what I set out to do. I really wanted to understand gravity together with quantum mechanics. And that has only been possible because of string theory. There's lots of progress that has been made, insights about black hole microscopically, but also the connections we've made with, well, using holography and maybe other fields of physics like condensed matter physics, quantum information theory. I think nowadays string theory is connected to so many topics that it's even a successful field in what it has achieved as in what kind of methods. I mean, if we ask for proof that it describes the real world, sort of experimental predictions, and there we can, that has always been a difficult thing for string theory, but doesn't mean that it has failed. I mean, I think we have established so much and seen so many breakthroughs and understanding of really fundamental issues in physics from string theory that I think already it has lived up to many of some of the promises at least. And so I feel happy about how the field is also progressing now. And I think we are indeed at a breakthrough moment where we're going to indeed understand the gravitational force in its connection with quantum mechanics in a fundamentally new way. And then it may be that we are going to be connecting indeed to observations in our universe, in the cosmology and so on. So, but this may be something that's, well, at this moment still around the corner, but I think we're moving in that direction. So I don't think that string theory is totally failed and so on. Maybe the initial promises of being able to predict, say, the mass of the electron and all of that, that we cannot sort of, well, claim that we will be doing. But that's not the only thing that came out of string theory. And I think there's still, as I said, many of things that will come out of string theory even in the future.
And so in the 1980s, one of the things, of course, that we would hold up as a community as the potential test of string theory that might happen in the next 10, 20 years was the discovery of supersymmetry, say at the Large Hadron Collider, because again, I think as many in our audience are familiar, the full name of string theory is superstring theory, and the super refers to this symmetric quality that the theory enjoys. It's not the only theory that can enjoy this extra symmetry called supersymmetry, but we anticipated finding new particles at the Large Hadron Collider that really would show evidence of this new symmetry. Partner particles for the electron called the selectron and squarks and so forth. Are you disappointed or surprised or just taken in stride that that has not as yet happened?
Now here I have to maybe go back to your first question about, well, the influence of Gerard at Hooft. Gerard also didn't really like supersymmetry so much. He actually liked the proposal that was made by Zumino and Wes, but the likelihood of discovering it, I always thought was sort of a coin flip. I mean, there was something chance that we could find it and maybe not. I mean, we wanted to solve some problems with the standard model. But I think that string theory has helped us to do many supersymmetry, I should say, in string theory has helped us do many calculations because it sort of helps us to make the theory more symmetric, as you say. But I also always felt that it may not be an essential agreement of the theory in the sense that there may be other ways in which we can sort of extend the framework of string theory that we don't need fully the supersymmetric formulation. Anyway, that was my perspective. I mean, of course, there was some disappointment, but it was not totally surprised, I have to say. I think that the chance of finding supersymmetry were always kind of a bit small. I think the other discovery, I think in our universe, the fact namely that there is a universe that's accelerated, has an accelerated expansion, the fact that we have dark energy in our universe, I think is also an important change compared to the early days of supersymmetry. If you talk about the 80s, at that moment, we were basically trying to prove there was no cosmological constant, as it's called, sort of that the universe was kind of flat. That was not the case. And so in the 90s, we discovered that there was this accelerated expansion. And that also turned out to be a problem a bit for string theory. So certainly string theory has now more challenges because, well, there's no supersymmetry. There is this positive cosmological constant or dark energy. And those seem difficult to sort of, well, in those situations, it's more difficult to apply string theory, and the calculations also become more cumbersome because you don't have the symmetry that we used. Like supersymmetry seems to be a very powerful tool also to do certain calculations.
And so I'm not even sure this is a really fair or well-defined question, but let me ask it anyway. Is there anything that you could imagine happening in string theoretic research that would cause you to say, I give up. I'm not going to follow any of this approach any longer?
Not really. What I do think is that what we have called string theory, with M theory and all of the dualities and so on, which is a very beautiful mathematical framework, that it may have a bit too much symmetry than our real world really needs. And maybe I have to give you an example. I mean, there are many, quantum field theory, which is the framework which we use for particle physics, also has very beautiful quantum field theories that have many symmetries, dualities. I mean, we usually call them conformal field theories. I mean, they are so nice, they are finite, they have many properties that string theory also has. But we also know they don't describe the real world. I mean, if we want to describe the standard model, we have to think a little bit bigger and extend those ideas. And so I feel that it may be possible that we have to do something similar with string theory, where we have to think a little bit broader and extend what we call string theory embedded in a larger class of. But I think the essential fundamental ideas that go into string theory will always survive. And I think they already have proven their value. And I already mentioned a bit this connection with quantum information that comes out. I think that's also where I feel that the most promising directions are, and that if we can understand what the role of string theory is in understanding, and connecting these topics like gravity and quantum information, I think that will become, a next maybe breakthrough. And I think that for me, string theory will always be a source of also inspiration, or maybe how should I say, is even a foundation of where we can find really what the microscopic theory of the world will look like.
And so I want to turn to those details in 1 second, but one final question along these lines. You've noted, and I think as many of our audience are familiar, that very difficult to experimentally test string theory. The energy scales at which it really flexes its muscles and distinguishes itself from known theories are either so enormous in the energy side, or the distance scales are so tiny on the length side that it's really beyond direct experimental reach. What people tend not to appreciate as fully, and perhaps you can just say a few words to this, that's going to be true of basically any theory that puts gravity and quantum mechanics together. It's not an intrinsically string theoretic obstacle, is it?
No, it's not. I mean, it's not like, if you think about Einstein equations or what Newton wrote down, there is a fundamental constant that plays a role, the Newton's constant. We also know that Planck introduced his Planck constants for quantum mechanics. Those are constants of nature that are very tiny, and they basically tell you that when you put them together, that the fundamental scale is so tiny that we can never sort of get there with any large accelerator or something like that. But I think that string theory also has shown, and also the way it sort of has been connecting to say like black holes, that there are certain surprises happening maybe even at larger distances. So I don't give up the fact that we cannot prove eventually or connect what string theory is doing to observations. But it's not going to be the thing at the Planck scale. I mean, any quantum gravity theory that sort of predicts something at the Planck scale cannot not be tested. And I don't think that that's also the area where we're going to be distinguishing between one theory and the other. I think it's also the fact that string theory has a, sort of this mathematical consistency that we use that makes me believe that for that, these other alternative theories will never do as well as that string theory is doing. But I am not pessimistic about finding eventually, especially in the cosmological setting, some predictions of string theory that we can really test and observe.
Yeah, exactly. All right, so let's now turn to black holes, as I think they're a nice way in to think about the work that ultimately leads to your proposals with entropic or emergent gravity. So if we can time travel even a little bit further back to the 1970s, when John Wheeler is posing various thought experiments to his student Jacob Bekenstein, Wheeler had a very genteel way of framing things. He asked what would happen if he took his nice warm cup of tea and threw it into a passing black hole. It would seem the disorder in the tea, the entropy in the tea would be gone. And he sort of challenged Jacob Bekenstein to try to figure out what would happen to the second law of thermodynamics if he could use black holes as these ultimate garbage cans that would be ultimate disposal mechanisms for entropy. So just give us a sense of what Bekenstein did with that, and then we'll move on to Hawking's follow-up.
Well, I really like that thought experiment, and I think it revealed a very deep fact about gravity and black holes in particular, because black holes are the ultimate objects where light cannot even escape. I mean, if you put all the mass together in this sort of sphere where the mass is so dense that not even light can escape, and suddenly we have this horizon around it. And what Bekenstein figured out is that when you throw something into the black hole, then the horizon size, of course, will increase because there's no more mass in the black hole. And so by thinking about these equations and doing a very clever thought experiment, he figured out that the entropy that a black hole has is actually proportional to its area. And so the area of the horizon. And so that increases. So when you throw in this cup of hot tea, I mean, indeed, the entropy will increase because the black hole gets bigger. And so you basically save also this second law of thermodynamics. And that idea, I think, is still, so central in what we're doing nowadays that I think it's the eye opener that sort of made clear that if you combine quantum mechanics, that because Bekenstein had to use quantum mechanical arguments to figure out what this increase was in the area and what is the amount of entropy that's being added to the black hole. It was later the calculation of Hawking that made it even more precise, of Hawking temperature. So then you get this object, a black hole, that has an entropy and a temperature. And suddenly we're seeing already, I think, what would be the first cracks in sort of what Einstein's theory is, because you're sort of seeing connections between thermodynamics and gravitational dynamics.
And so how important, or surprising perhaps is a better way of putting it, is it that the entropy that a black hole contains is proportional to the surface area of the event horizon as opposed to proportional to the volume of what's inside?
Well, it's very important because it actually is very different than any other thing that we know about. Because if you think about what people did in the 19th century when they developed thermodynamics, they thought about gases or hot fluids, and they have molecules and they move around. And they also have an entropy, because the entropy is sort of a measure of the amount of chaos and motion of all these atoms. And that grows like the volume. For any material, if you heat it up and you ask, well, what happens to the entropy? It will increase, but it will increase proportional to the volume. It's like in any object has then some entropy density. So black holes are very different. I mean, there you see that the object gets bigger, but the amount of entropy doesn't grow like the volume, but it grows like this area. And it also tells you, therefore, that the amount of information that can be contained in that part of space-time should grow like the area of its boundary. I mean, this eventually led to ideas of holography or the holographic principle. Actually, Gerard Hooft was actually one of the people involved in calling that principle, and also Lenny Susskind. And so they made clear that this idea that the maximum amount of information that you can put in, or entropy that you can associate to a region of space, is when you put in energy to the point where you have a black hole. That means that this maximum is given by the area of that object, of that part of space. And that, well, again, has influenced our thinking so much in the last, well, 2-3 decades that I think it's one of the bigger discoveries, which I think we took from the 20th century into the 21st century and are still figuring out what it really means.
Do you have an intuition that you can share that can give us a quick, intuitive way of understanding why the entropy is carried by the area and not the volume?
I have some intuition, but then I think we have to take a little bit of a step, because the way that Hawking also entered in this topic was, namely, first he didn't believe Bekenstein. So he wanted to check whether it was correct, yes or no. And so he started calculating, and then he suddenly discovered, because what he said, well, if it has an entropy, a black hole also have to have a temperature. So Hawking discovered that black holes radiate indeed particles with a certain temperature, but it happens sort of because of quantum mechanics. I mean, quantum mechanical uncertainty has the effect that, namely, energy can be uncertain, and therefore particles can pop out of the vacuum in pairs and they're annihilate again. But in black holes, what can happen is that one of the particles drops in and the other one gets out. And then you see this radiation coming out with a certain temperature. But this process tells us also what maybe the meaning of this entropy is and why it goes like the area. Because each particle that gets out has a property like a spin or a charge, but then the other particle that falls in must have the opposite property. So the spin must be, if the one particle has spin up, the other one must be spin down. Or if the charge is positive, the other one must be negative. In quantum mechanics, this means these particles are entangled. So this entropy that we're counting says something about the amount of entanglement between what's on the outside and what's on the inside. And so I think about this area law as really telling us that if I think about cutting, say, space into 2 parts, the right-hand side knows about the left-hand side because they're entangled. And you have to think about entanglement as something that acts really at large distances, and things can be far away. But you count entanglements basically as sort of lines that are piercing through this surface. So there's some way that you're cutting the space into 2, and that you're cutting the entanglement between the left and the right. And that's the amount of information that we're counting.
Right.
So then there's some way that we know that there must be an area there. And this turns out to be, well, one of the bigger central themes of our current thinking. I mean, this is also where string theory played a role in making that even more precise. I think there we have been able to really describe microscopically and explain how this area law sort of emerges indeed from this microscopic description.
So you made reference to Hooft and also Susskind as well, who in those early days introduced this notion of holography, this idea that you could have physics on a surface that somehow captures the fundamental degrees of freedom and describes everything that could be happening in the volume, even though it's only taken place on the surface. And of course, a hologram is analogous to that. You know, a thin piece of plastic, you illuminate it correctly, it yields a realistic three-dimensional image. And so would you consider black holes as an example of this broader principle that perhaps applies to physics everywhere in some sense, that volume physics should always be fundamentally described as area physics?
I think in many circumstances, yes. I mean, this is sort of what this holographic principle is telling us. And we have now indeed found examples. I mean, already alluded to string theory as having given an explanation of this. Maybe I have to explain a little bit more about that. One of the lessons I learned from string theory, and actually I think is one of the more important one, is that it tells us that there's sort of a microscopic description and a macroscopic one. I mean, you know, in string theory, we can have strings that are vibrating, and a very important distinction between strings of two kinds is namely you have the closed strings. They don't have endpoints, but there's also something called open strings, and they have endpoints. And it seems like the microscopic description always is in terms of the open strings. And so we have learned that there's some way of describing the same physics in two ways. One, in terms of these open strings, which doesn't involve gravity, because this gravitational force actually is mediated by these closed strings. And so the microscopic description that we, for instance, we can find for black holes is one where we use only open strings. And so there's one way that we have found a microscopic description of black holes that explains that the entropy goes like the area. And so by studying this further, people also found, and this is a big discovery of Juan Maldacena, that there is actually a microscopic description of a space-time that is, you can think about as describing what happens very close to the horizon of black holes, where the microscopic theory really lives on the boundary of that space-time. It's a space-time that we don't live in. It's called anti-de Sitter space. It doesn't have dark energy, for instance. And there you have indeed a theory that is living on the boundary, really like a hologram. And it has no gravity in it, but if you then calculate things, you find that it's exactly sort of equivalent to a theory that lives in the space-time with gravitational force, everything like that. I see this also kind of as an evidence of the emergence of the gravitational force, because the microscopic theory is really the theory that lives on the boundary, described in this sort of this open string language, while the closed strings are then sort of emerging when we go to sort of a more effective macroscopic description. So I think, that's for me a way indeed to think about maybe even physics in our world. I mean, if we think about what happens in this space around us, I do believe there is a certain description that's microscopic that lives on the boundary of that certain part of my space. And this holographic principle might be one of those principles that's valid more generally than just what we have now discovered up to now. I mean, we like to sort of have this also valid in our universe.
And so will you call it a philosophical prejudice, or is there a more fundamental way of distinguishing these two theories? You describe the boundary theory, the area theory, the open string description as the more fundamental, and then the volume theory, which has gravity, as the emergent theory. How do you decide who's emergent and who's fundamental?
Yeah, that's a good question, where I do think that people were maybe a little too quick in calling it a duality. I really think that what we mean by the theory in the space-time is this theory that we haven't fully discovered yet. Namely, it's the full string theory that should be non-perturbatively defined and everything like that. I think our current description of what's happening in the space-time is using Einstein's equations and so on, which we know are kind of only describing what happens at low energy. So I think that what we call that they might be equivalent. I think that what we should think about is that there's not a microscopic theory, is really the full theory. So if you write down the Hilbert's, well, the quantum mechanical description, I should say, with all the things that we know about quantum mechanics, that's usually the one that we apply on the boundary. I mean, in this open string language. And then by doing some averaging, some coarse graining and things like that, we end up with this bulk description. I think most people now agree that there's some, well, you throw a bit away from the microscopic theory in order to arrive at what we call the gravitational description. Right. The other thing that I have to say, and that goes back to your earlier question, is that in that context, we also have been able sort of to really derive the Einstein equations. I mean, what I mentioned is this connection with entanglement and areas has something that has been very precisely verified in that context. I mean, there you have a microscopic description on the boundary, and you can ask how much entanglement entropy, I mean, how is a certain region of the space entangled with its outside, and you find exactly again that is given by that area. So the area law or the equations that Bekenstein and Hawking derived suddenly got another interpretation in this theory, namely as an entanglement of the vacuum. I mean, even empty space has entanglement in it. And already in it, and that entanglement grows like the area. So there's some very fundamental thing that we discovered about space-time and its connection with quantum entanglement. And that is indeed where even this whole ideas of emergence of gravity sort of come from. Because this entanglement entropy satisfies the same laws as the laws of thermodynamics. I mean, in the laws of thermodynamics, we know that if we add a bit of energy to the system, the entropy will increase. And that's what we call the first law of thermodynamics. And it turns out that if you write down that equation and if you assume that the entanglement entropy goes like the area, you end up with Einstein's equation.
And so can we unpack that a little bit just in a couple of steps? So you describe Bekenstein and Hawking, the work that begins to show that black holes have this unexpected thermodynamic quality to them. Then a little bit later, people like Ted Jacobson come along and start to think. So what was Jacobson's insight? And then we can transition to the work that you've been doing.
No, excellent. This is, I think already Bekenstein and Hawking and people that were thinking about black holes discovered that the laws that we know about black holes can be written down in the same form as the thermodynamic equations. So then Hooft and Susskind proposed this holographic principle, and Ted Jacobson was very quick in realizing that if you take that as a principle, that the area sort of measures for any part of space-time some kind of information, and he already realized it might be entanglement entropy. Then he said, well, if I assume that that amount of entanglement is equal to the area, and I measure it in some units, we don't know what they are yet, but let's call it G Newton or something like that. But then what he showed is that if I take the first law of thermodynamics, namely that if I throw some energy across that surface and that it somehow changes its area, he showed directly that you get the Einstein equations from that. So he said the Einstein equation is a consequence of thermodynamics. And instead of the other way around, I mean, so Einstein's equation basically are derived by assuming that the amount of entanglement is equal to the area. And I think that was
but Erik, can I ask you one question right there? So, and again, this is probably my own ignorance because I've not studied these things sufficiently deeply. But when I've read Jacobson's paper and subsequent papers, I'm always impressed by exactly what you describe, how Einstein's equations emerge from a different starting point, from a more thermodynamic starting point. But then after I leave the paper and a few days go by and I don't think about it deeply enough, I begin to ask myself, is that deep or is it trivial? In other words, if you can start with Einstein and then a la Bekenstein, Hawking, and others get to a thermodynamic like description of what's going on, are you simply reversing the sequence of implications to go backward, something that you would expect to be able to do? Or is it somehow deeper than that?
So this is where I think indeed why my paper actually I think is different than what Jacobson does. And I think also where my point of view differs from what other people say. Because one of the things, you are right, by the way. So that what they have done is that if you assume Einstein's equations, you play with these thought experiments of Bekenstein, then you get to the conclusion that the entanglement goes like the area. Now I assume that the entanglement goes like the area, and I reverse all the steps, I get Einstein's equations. But what this shows you is that there is assumption made that the entanglement goes like the area. And you were asking me, do I believe that's true everywhere? I don't believe that's true everywhere. So if I change the assumptions, I change the equations. So Einstein's equation is a consequence of the fact of assuming that the entanglement entropy goes like the area. And then it kind of becomes trivial, and you might worry, well, what do I learn? Because I get simply Einstein's equations. But what you have learned is that the Einstein's equations are emergent. You have to derive them. And you have to derive them, and you have to derive them from a very special stuff that we call space-time. And that space-time has apparently very special properties in such a way that entropies go like areas. And that's what makes space-time different from other materials. We discussed that the area law is strange, so space-time is strange because it has this area law. But I claim it doesn't have area law in all situations. And then the equations you would derive from the same kind of arguments will look different.
And can you be concrete about what some other equations would be like and the variation from the area law that yields those equations?
Yeah, let me be very concrete. I think we have indeed now found a very special universe in our string theory world, namely this anti-de Sitter space with this holographic boundary, where we have verified that the entanglement entropy goes like the area, and that we can derive again Einstein's equations. Very precise. People have done this, people like Rob Myers. Mark von Ramsung, by the way, played a very important role because he sort of emphasized the fact that this entanglement entropy is kind of what makes space-time hang together. He sort of said, well, if we break this entanglement, then basically these areas are shrinking, and I kind of break up the space-time into its part. I mean, also the whole black hole information paradox has played a very important role, which sort of a consequence of Hawking's discovery. But we don't live in that space-time. That space-time that we have now verified all these things in has no dark energy.
Right.
And microscopically, we also know that space-time, well, it has a vacuum state indeed that satisfies all this entanglement entropy, but it's really the ground state of that theory. Our universe is different. We have a dark energy in there. We have an expansion, which also means that if you see things moving away from us with an acceleration and faster if we go further out, that we have sort of an effective horizon, namely certain distance there will be things moving away from us even faster than the speed of light. So there's some horizon to our own universe. So the same arguments that Bekenstein and Hawking used tells us that our universe also has an entropy. Our universe also has a temperature. So if you then ask what is the stuff that the space-time is made of, it's the same stuff that this other universe was made of. I claim it's not. Namely, there's dark energy in there. And if you ask what is now the source of the entropy of our universe, we know exactly, we can calculate again how much entropy our universe has. You take this expansion of the universe, it's described by what we call Hubble constant. It's the Hubble expansion that also tells us how far this horizon should be. I can then calculate what is the area of that horizon. And then I can measure this in the same units that Bekenstein and Hawking did, and you get to a huge number, something like 10 to the 122 or something like that. It's a very large amount of information or entropy that's inside our universe. But how did it end up there? I'm saying it's because indeed the universe is different. So first of all, having a temperature and an entropy already tells you that it cannot be sort of like a single state or a single, I mean, it does have some motion or something, things are going on. So the amount of entropy, as I said, is very large. The other thing I want to say is that there's dark energy in the system. So I claim that this entropy is actually caused by the presence of dark energy. So dark energy is this mysterious energy in our universe that's everywhere. I mean, it's really everywhere in space. And so it's not just sitting on the boundary or something like that, it's everywhere. So what I'm proposing, and actually that's what I wrote a paper on, is that in our universe, there's also an entropy that really grows like the volume. It's namely an entropy that we should associate to the dark energy. So the assumption that we use to derive Einstein's equation is not valid in our universe, and it's associated to Hubble constant. The Hubble expansion tells us how much entropy there is in the vacuum as a volume entropy. If you start using that and start redoing what we did in deriving the Einstein equations, you find that there is a modification happening at a certain scale. Turns out if you calculate that scale, it's exactly the scale inside our galaxies where we see that Newton's equations and Einstein's equations fail to describe what is going on. The only way we can fix Newton's equation and Einstein's equation is to assume some enormous amount of mysterious matter that we haven't seen. And well, it's called dark matter, but it's an assumption. And I think it's just there to fix the equations. Because if you really derive the correct gravitational laws from this modified assumption, namely that there's not just an area law, you'll find that you can explain what's happening in those galaxies.
And so maybe we can unpack that a little bit, because you mentioned something that to most people's ears may sound strange, even though I think they've heard it in different language. You said at the scales at which Newton's equations and Einstein's equations fail, we often don't hear them failing, but of course we do know that there is an issue with the rotation curves of galaxies, which I presume is what you're making reference to, that the traditional description based on what we see doesn't describe the motion of the stars in those galaxies.
Yes. No, that's correct. So if you only use the amount of matter that we see, and you would plug that into the Einstein equations or the equations that Newton wrote down, I mean, in those circumstances, you don't really need to use Einstein's equations. But anyway, they will tell you indeed that the stars, well, they rotate too fast. I mean, they should be rotating slower, and that they rotate so fast that they should actually fly away. So the only way to keep them inside the galaxy is to assume that there's more matter than that we can see. So this is seen as evidence for the existence of dark matter. I mean, but if you're really honest, I mean, it's something that we add to the theory in order to make it work. I mean, and of course, there are other ways in which dark matter plays a role. I mean, if you ask, I mean, how did these galaxies form? If you think about the expansion of the universe, we need them to sort of, well, coalesce and make objects that are compact. I mean, then this dark matter also plays a role. So, I mean, nowadays, cosmologists believe that there is this dark matter out there that is really just matter with a certain density that is, well, even larger than the amount of matter that we can see. So if you ask how much matter haven't we seen, I think it's about whatever 70 or 80% more than what we have seen. And so there's a lot of search to find these dark matter particles. If they're particles, they may be something else. Maybe they're even tiny black holes. But there's also this other option, namely that if you see something where your equations need something that, well, we don't see, then you may wonder whether the equations are the correct one. I mean, there's, of course, the famous example for, well, there's one that worked. I mean, I think they found
Neptune,
one
I
of
guess.
the Neptune, I think, by doing this. But then they tried to do what happened with Mercury, which is also doing funny things. And then they thought there may be some other planet that explains that. Anyway,
Vulcan.
that
They
turned
called
out
it
that was
Vulcan, I
the
believe. Yeah.
Vulcan. That's right. But anyway,
Yeah.
that was the kind of dark matter that didn't exist. I mean, there's
Yeah.
some way. So trying to fix a theory by adding matter sometimes works and sometimes doesn't work.
And so in this particular case, you're suggesting that this long-standing belief among the whole community of physicists, for the most part, and astronomers, that dark matter is the explanation for the additional gravity that keeps those stars from flying out of their orbit. You're saying that your approach naturally gives a modification to the gravity equations that would not require this dark matter at all.
Yes, that's what I'm saying indeed. But well, admittedly, what I have done is first of all made an argument where this change will happen. And I found indeed that is at the correct scale. There's a certain phenomenology that people have applied to, because what actually happens is kind of that the velocity has to decrease in normal Newtonian gravity as a function of the distance, but people see indeed that the velocity stays constant. That's what you say is these flattening rotation curves. I mean, that tells you something about the amount of dark matter that's required to explain exactly that flattening. And it turns out that there's some parameterization of that I was able to reproduce from these arguments. But
and is
I
that a
have to admit,
reproduction of MON, the modified Newtonian
yeah, so
dynamics?
this phenomenology is called modified Newtonian dynamics. It basically tells you what the change in the power law should be. So I find that using the additional force that comes from this volume law, you can explain that what I would call Mondian phenomenology. It's sort of like more a modeling of what is going on. I don't treat it as a theory because the way I find it is not by a modification of simply a force law. I mean, I find this a very naive way of even solving problems because I always say that Einstein didn't take Einstein's equations and simply modified them a little bit by adding a term. He had a completely new theory. And I think that's also what I'm proposing here is not a modification of the laws that we have, but basically a much more fundamental understanding of where it comes from. And then these additional effects must sort of be explained in that theory.
So just to give people a sense of where this modification would kick in, you noted that it's really when gravity is extremely weak relative to the gravity that we experience. I've seen little calculations. I've fiddled myself just to get an intuition for it. I think there's one example. If the Earth's gravity were as weak as the gravity that you're describing, and you drop something from like a meter above the surface of the Earth with that new weak gravity, it would take something like, I don't know, many, many hours, like 30 hours or something, for that object to actually cross the 1 meter. That's how weak the gravity is in this domain. Is that a reasonable?
Oh yeah. I think that is correct. I mean, but that acceleration that is required there actually has a nice way of even describing it, because one of the things that we learned of this physics of horizons is that even near a horizon, near a black hole, there's also an acceleration, namely you fall in. And also our cosmological horizon, if you ask, well, what's happening at the cosmological horizon, there's also an acceleration if you cross it there. Hawking's calculation actually, and it's also even in empty space, there's a connection between this acceleration and the temperature that Hawking computed. I mean, so there's a way you can express this temperature in terms of this acceleration. So also our universe has a temperature that's expressed in some acceleration that can be measured near the cosmological horizon. that is exactly the same acceleration is where the rotation curve starts flattening. So seems to be a connection between that scale and the cosmological expansion. That's kind of what I thought was sort of almost, I would say, well, when I heard about it and I had already some ideas, I thought, well, that must be sort of a smoking gun almost, because I think the fact that there is a dark energy has to do with this acceleration. And also the fact that this is going to change gravitational laws exactly at that acceleration scale, I thought was too much of a coincidence. And that's also where I found that my argument of having a volume contribution to the entropy gave me exactly that scale.
Just so I understand completely, you are putting in the dark energy scale that emerges from observations. That's not something that you're able
You
to have
can
a
derive.
fundamental explanation for.
No, actually, that's correct, because there's some way in which that scale has to do with, I mean, we talked about this very tiny scale in gravity, which is sort of the Planck scale. In our universe, we also have a very big scale, which is the size of our universe. I don't have a way of deriving the size of our universe, because it actually, what it does is, I mean, it actually tells us how much information is there in our universe, because the size of this horizon is what gives us, well, information about where the horizon is located. That is derived from Hubble constant. So I'm not deriving what Hubble constant is. For me, it's a new parameter, say, in the theory that will predict where that acceleration will occur.
And so if this idea were to stand the test of time, it would suggest that we've been misguided perhaps in thinking that we've been much like the scientists who introduced Vulcan, not like the scientists who introduced Neptune, in terms of trying to understand things. But dark matter has so many other roles besides the rotation curves of galaxies. It comes into understanding the microwave background radiation, the large scale structure of the universe, the formation of galaxies, the bullet cluster. There are all these, and we could unpack as many of these as you'd like. Do you do well in trying to explain these other instances where dark matter has been invoked?
So what I think happens is that the modifications that I'm talking about sort of can be parameterized in sort of an effective dark matter, in the sense that there's some way that the influences of this volume contribution can behave in these circumstances as if there is some dark matter. I certainly thought about what it has, I mean, for instance, for the what we call this cosmic microwave background. So there are some ways that we can observe how much light comes from the early Big Bang. And there's tiny fluctuations. In order to explain that, people need also to assume this dark matter. I mean, that's a calculation that I certainly try to do, but there's other things about the cosmological evolution, for instance, that people know a lot about the early universe because of this cosmic microwave background. They also can observe things nowadays by looking at redshifts and see how far things are moving away, or how fast things are moving away. So they can measure, for instance, the Hubble constant. One of the problems people are now running in is that when they do it in these measurements and they do it with the early universe, is that there's a slight mismatch. This is called the Hubble tension. So I thought about trying to see if I can connect it to that. And one of the important tests for me is indeed that the effective dark matter that I have can explain both what happens in the CMB time as well as the present day sort of observations in galaxies and clusters. And that can work, but the cosmological evolution indeed can be different. So I think there are ways of testing this.
Wait, can I understand that more fully? Are you saying this may be work that I'm not at all familiar with, but are you saying that you can connect the values of the Hubble constant that emerged from early universe studies, which is usually, a different number by 5% or so from that emerged from later universe studies, that so-called Hubble tension, you can connect those?
Well, in the way I can model this, yes. I mean, but I have to admit that I find explaining the CMB data a very important one. But you're right. I mean, the theory that I have now is not yet at the stage where I can really match all these other uh, calculations that people have done. So I think that the current best parameterizations of the data is certainly the dark matter paradigm that people have now still in cosmology. But it doesn't mean that the actual reason is that it's a particle or something like that. Because if you look at how it's being used, it's just some uniform, well, it's some density which can do certain things, but never in those equations is being assumed that it's a particle or something like that. I mean,
Right.
it can be anything. I mean, it can be even some blobby thing that we don't know yet. I mean, and sometimes I think that well, assuming that it's a particle is because we know particles, but having so much more that we haven't seen, maybe it's some totally different kind of entity.
Yeah.
But as I said, I mean, I think that we have to understand gravity in this universe with dark energy in the same way that we have done it for this universe without the dark energy. And that there I feel that the theoretical well progress that we need to make has to go in that direction. So I don't claim to have the full theory there because I don't
Right.
have this microscopic model of our universe that we have for this other universe. So my current research is mostly directed to finding a similar microscopic description as we know for this anti-de Sitter space that has this hologram, but now find a microscopic description of what we call de Sitter space, which has this energy in it. And I'm happy to see that many researchers, even very young researchers just entering the field, are seeing this also as one of the main problems, that you have to find now ways of finding similar microscopic descriptions of, well, this positively curved space-time as we had first for the negatively one. And then I think that this question about what is then explaining the entropy, or what is explaining that there is a horizon, what explains there is this curvature, will indeed sort of lead to the same kind of conclusions that I already had, namely that there is more to the entropy in this universe than uh, well, than we have thought about
Sure.
before.
Now your work has certainly inspired over the last decade a number of groups to undertake, experimental studies of large numbers of galaxies, seeing the degree to which your approach can do a good job of modeling their particular motion and structure and so forth. What's your take on those studies? Do you think they're too early? I mean, some would look at those studies and say, we're not so clear that Verlinde's approach is really working. Or some would say, no, it works in this particular case. What's your stance on that?
No, I think they're preliminary in the sense that one should wait until the theory is more fully developed, because one of the important assumptions I made in sort of my calculations is again simplifications like spherical symmetry, that things are sort of kind of static, not too much dynamics. But also, just admittedly, I don't have this full microscopic theory, and there are many questions or steps in my calculations that were done using some assumptions that I like to establish better from a theory perspective. And so I don't have a full theory that can be compared yet to experiment. I find namely the already that I can reproduce current observations already a step. It's not like that my theory is ready to be tested in all circumstances. I mean, this is where I feel that this is too early, and I really prefer to have time to develop the theory than to sort of already have to answer questions about, well, if I put this equation and compare it to some measurement, it doesn't work. I think that's not really what the point was even of what I wrote in that paper. I mean, it's more
Right.
like yeah, you're trying to sort of get the qualitative behavior, but quantitatively there might still be many things that we need to figure out more precisely.
Right. And so going back to some of our earlier discussion, to what extent would you say that string theory is playing a role in this work? Is it inspirational, motivational, or do you really feel that it's intrinsically vital to the ideas that you're developing?
I think it's intrinsic in the sense that mean, I mentioned already how we are able to explain things like entropy that grow like areas. I mean, sort of we have some holographic models. One of the important lessons I found when, I mean, maybe I have to mention the work of Strominger and Vava when they calculated the entropy of black holes. I mean, these black holes were not tiny objects, not of the Planck size. They're really big things. They can sort of explain entropy. And then you have to ask, well, how was that even possible? And they found, I mean, this is of course also the work of Polzinski, these objects called D-branes and so on, that we learned that string theory is about many more things than just strings. I mean, there are many other things happening. And so in that, if you look at those extended objects and look at how they describe, well, the entropy of this black hole, you find that it's not just particles that are really doing it. I mean, string theory is about many more things than just particles. It's about strings, but also about objects we call long strings. There are indeed these D-branes, or even in this holographic theory, we also know that there is indeed more than just the particles in the bulk. On the boundary, we have this open string theory that is a gauge theory, which has many more degrees of freedom. We call this, well, n being large. So I think the fact that string theory is teaching us that there's this microscopic description, which has many more degrees of freedom and different kind of degrees of freedom than what ordinary particles look like. I think that is teaching us something about maybe what we need also to describe this dark energy. So I really want to have a microscopic model of the dark energy as having a dynamics of its own, having an explanation of why it has an entropy. I want to explain the entropy of the Sitter space in the same way that Vava and Strominger explained the entropy of black holes. And I think the same mechanisms will play a role. So I indeed use it as inspiration to look at what we learned from string theory. How did we explain the entropy that grows like the area? How did we explain the black hole entropies? And then say we're going to use the same ideas and apply that to the Sitter space. And so I think a model of the Sitter space, a microscopic description of the Sitter space in string theory, of along the lines of string theory, is going to be the next thing that we need to connect my ideas about dark energy and dark matter also to this more microscopic full theory. And I think string theory will play an essential role in doing that, because it's exactly those same ingredients that are required to explain this entropy of the dark energy.
And so the work that you've been doing so far, does it give you any insight into the question of whether the dark energy is truly a constant or something that is dynamical and will either grow or decay over time?
That's a good question. Actually, I mean, I talked about the Sitter space, and then generally I think about the Sitter space as not the one that we usually talk about, which is sort of exponentially growing. I mean, there's a way of looking at the Sitter space where you basically say, well, I sit in one place and then things are there. There's just dark energy and everything stays the same. So I find dynamics difficult to compute. Actually, I think, but what I do believe is that the dark energy has a dynamics in itself. It doesn't mean that it doesn't need to be constant everywhere. I think there's a certain motion, a certain degrees of freedom that are filling the universe, that are doing things while we're not looking at it. I mean, it's dark for us, but anyway, there may be a dynamics that we are not aware of. Whether it's diluting in the same way as Einstein would have said. I mean, I think effectively, yes, probably, but it's not just a constant. I don't think of, I mean, there I do like the name dark energy more than the cosmological constant, because the cosmological constant was just a parameter that Einstein put in his equations, just also to describe cosmology. That's why it's called the cosmological constant. But for me, it's a dynamical thing. And so having a dynamics in time would be interesting, but it's not something that I have already, well, established that it has to happen in my theory. So I don't know. I mean, it's something that I find intriguing. So I'm watching indeed closely what these new observations with Euclid and so on are doing. I mean, if we can define more about what the equation of state, what's then called of dark energy is, I find that very interesting, but it's not like I have a theoretical prediction to make.
Right. Now, one of the other things that famously emerges from trying to understand the dark energy, or in particular its value, you in essence made reference to its value, that, that 10 to the minus 122 that you mentioned earlier when talking about the area of the cosmological horizon. People have invoked this idea of a multiverse to try to give some insight into those values. The idea of roughly being, if you have a strange number that you want to explain and you're having trouble explaining it in a single universe, if you imagine you've got an enormous number of universes, each with a different value of that strange number you're trying to explain, if there are enough universes, then you can establish pretty easily that there are going to be at least some, in fact, many that have that weird value. And then you simply posit that you're in one of those universes, and that's why you see the particular weird value that you do. Do these ideas repel you, attract you? Or what's your take on the multiverse and trying to understand dark energy?
I mean, there's certainly clever people that have proposed these ideas, but I don't like them myself so much, because you have to talk about all these things that we can never observe or never can interact with. And also, I'm less bothered by this big number, this strange number. I think I'm kind of more like Dirac, who famously said, well, we're allowed to have one big number in our universe. It's the age of the universe. And I feel that this big number says something about the complexity of our universe. I mean, how many things are possible? So this 10 to the 122, that's what we have to do with. That's the amount of information that we can use in our universe. And therefore, I feel that big number might be just given to us. And then I proceed from there. I don't think that that's a number that I can explain. And that also goes back to your earlier question. So I need these two scales in my theory, the Planck scale and this other very big scale. And the relative size between them is not something that I can compute. I feel that I'm willing to do that. I mean, I think that's even maybe as humans, we should be a little more, how should I say this, not thinking that we can answer all questions about the universe. I think there's some ways that we should be happy with how much we already understood, and thinking about explaining this one thing that we maybe don't understand. I'm not unhappy about that. So I'm not someone that will work on multiverse theories, because I think that's not something that attracts me, indeed, thinking about these universes that we don't see anyway.
Now, one of the qualities that emerges from entanglement, and it was actually one of the qualities that troubled Einstein the most, is this notion of some level of non-locality in our understanding of physics. And as things have progressed, especially in the work that you're describing and others in the same universe of ideas have been developing, it seems like non-locality has become ever more present in our thinking about the universe. I mean, holography itself, perhaps you can just describe, involves a level of non-locality. So where do you come down on non-locality? Maybe starting with the more easy kind of entanglement and then moving to some of the more dramatic versions that emerge with holography.
I'm actually okay with non-locality, as long as it's not acausal. I mean, what causality is something that one thing that happens influence what's in the future, and that you can also have things, well, going backwards in time or something like that. That I find a very important principle, but non-locality, like the one we have in entanglement, doesn't bother me. I think it's quite essential to the existence of our universe. I feel that I mean, that's sort of the recent ideas of what's called this
But
Einstein and Rosen.
Should Einstein have not been? Do you understand why Einstein was so troubled with what we would now view as the most modest kind of non-locality, namely basic quantum entanglement?
I understand his way of thinking, but of course he came from a period when things were, well, not so strange yet, as in we now know that quantum mechanics is. We have a new generation of physicists that grew up that got used to it. So for me, it isn't less bothersome. But I understand his intuition. I think it's a very clever argument they gave. I mean, he wrote this paper with Einstein, Podolsky, and Rosen, and I think it was in the 30s, that he was not happy with his non-locality. But nowadays, entanglement is really what makes quantum mechanics work. If we talk about quantum computers, the quantum internet, all these big revolutions that will be coming in quantum technology, that all comes from entanglement. So it's sort of the essence of what quantum mechanics is. And this also tells us about that the world indeed is much less local than we have thought about before. This is also why I think that our language of thinking about nature has changed. I mean, I do think that the 20th century is really about space-time, particles, forces. That's 20th century physics. Nowadays, it's information, quantum entanglement, a very different worldview even about what is really the fundamental building blocks. It's no particles, now it's qubits. It's things that are sort of the fundamental notions of quantum information seems to be the things that we have to build everything from. And that's also because of our technological progress. From technology, we learn a different language. And that's also the way I think that our worldview will change. So having this ultra local picture that a particle can only influence the particle that's next to it or something like that. Now it seems like there are things connected to each other through entanglement, that something that happens here may influence what's happened there. And I think that's beautiful. I think that somehow I like that way. It's also because I think that's really what makes space-time kind of emerge. I think that idea of Van Raamsdonck, that entanglement is also what makes space-time sort of connected. I like that a lot. I think that, or just EPR is ER, that's sort of the new name for it. That was given by Maldacena and Susskind. So where EPR stands for Einstein, Podolsky, Rosen. And the funny thing is that Einstein and Rosen also thought about black holes and seeing them sort of connected to other universes through some wormholes. And so that's
2 months apart. Those papers are 2 months apart in 1935.
yeah, that's why. I mean, there was a certain period that Einstein worked with Rosen, and apparently he thought about two things that we now know are intimately connected. I think this is where I feel that indeed there's some irony in there, because I think it's also the thing that makes eventually Einstein's theory being replaced by something else, namely understanding space-time and gravitation from quantum entanglement. And he made a contribution to that, a
No,
very important one.
No, it's a deep and strange and wonderful connection. But I just want to follow up on a comment that you made, which is something that I have thought a lot about from time to time. We as physicists tend to use, maybe that's even the wrong way of framing it. That's describing it as a causal, but there's a correlation, at least, between the technology of the day and the metaphors that we use to describe our physics, right? I mean, in Newton's time, you had, mechanical
Cannonballs,
objects, clockwork, you had the
cannonballs.
mechanical universe,
Yeah.
and then as we go forward with other kinds of technologies, we begin to sort of think of them and now we're in the quantum age, obviously. The technology is all in the quantum computing direction. And lo and behold, the physicists are describing the universe as a quantum information processing system and using quantum error correcting code to map, say, the degrees of freedom in a volume to those on a surface and vice versa. So what is driving what here? Is it coincidence that we tend to always use the technology of the moment? Is the technology coming from the physics, and therefore there's no surprise that the physicists would be using it? How do you think about the language and the metaphors and really the working framework? It's more than just metaphorical. We actually invoke the mathematics of the technology within our physical theories now.
No, but I think this is the beauty of how humans make progress in science and technology. I see this hand in hand. I think there's some way that technology drives science and how science drives technology. And it has to do also with our experimental capabilities. I mean, if you want to build some big thing that tests particles, we use technology all the time, but also, so there's an interaction between technology and the scientific language. So what you just said about Newton in a mechanical time with cannonballs and things like that, his thought experiments use these things. And so he wrote down laws that describes this. I mean, when people invented steam engines, they started thinking about thermodynamics and about what's flowing there, and then the atoms came and all these things. So I think there is indeed a hand in hand, and I think it's also because our language indeed progresses, and I think we as humans can eventually, well, we learn from the past, from our predecessors and so on, but then we use. So you should never sort of forget about what you have learned. You should always understand the previous layer in terms of the next one. So I think we should not just throw away the language that we had of particles and forces and so on, but have a better understanding. I think in that sense, I think there's a deeper layer that we are going, where we have still the old theories. I mean, Einstein's theory will not be thrown away, just like Newton's theory wasn't thrown away. I mean, it's not like Newton was wrong, because if we want to shoot something to the moon, we still use Newton's equations. And so Einstein just extended it. And this is also where I feel that we now are extending what Einstein was doing, but in this new language, the language that we are now using with quantum information, other notions.
So how then, using this language, somewhat unfair question, but how would you encourage a new mindset? In other words, do you think about the universe as ultimately made up of information carrying entities, and their interactions are nothing but some kind of quantum information processing? Should we really think about reality in that kind of language?
Well, maybe, well, I don't think that we can ever figure out what all that information is. So I think in that sense, we are a little bit like in for the 19th century, when people didn't know that atoms really existed or molecules. What I do think is important is to just realize that the theories that we have now, I mean, which are most successful, like Einstein's theory and so on, that there is a deeper understanding of them. So this word that you mentioned in the beginning, emergence. So I do think that a different way of thinking about our universe, that our current description should be thought about as emerging from something that's more microscopic. Even notions about space and time and motion and all these things, you should think about them that there is some microscopic explanation of them that may not be the same one that we have before. I mean, so the fundamental nature indeed of forces, for instance, like the gravitational force and even the other forces in nature. So actually, when you said, I mean, gravity may be different because it may not be sort of so fundamental, I think eventually all forces then have the same status, because there's some way we have to explain their emergence as well. So I do think that emergence is a new way of looking at the universe. And when I started like this 40 years ago, I grew up at a time when people said, well, we're going to find a theory of everything, and eventually we're going to explain everything from a very reductionist point of view. We're going to know what's happening at the Planck scale, and then we build up everything, and we know what's happening at a larger scale because of sort of a reductionist point of view. I think emergence is more subtle, because there's some way in which things can emerge that has nothing to do with reductionism or something like that. I mean, this idea of entanglement, for instance, is this large scale, I mean, this non-local nature of the microscopic world, I think is also telling us that we cannot explain everything by going only to the very tiny thing. You also have to connect it to the large
but taking this discussion, taking it a little bit full circle, early on, I asked you a question about Gerard 't Hooft and his views on string theory and the influence it may have had on you decades ago. 't Hooft has also been working, as I understand it, I've not followed it in detail, on showing that quantum mechanics emerges from something deeper, a kind of Einsteinian vision that quantum mechanics has all this weirdness only because it's a provisional theory, and the deeper understanding, once you find it, will not have all this weirdness. You'll recognize that the weirdness only emerged because you were using this higher level provisional description. Does that ring true to you?
I don't know, actually. Here I have to admit that indeed 't Hooft and Einstein have very similar views, that this idea that there's this probability that the things that in quantum mechanics we cannot really predict, but we have only probabilistic outcomes. Hooft doesn't like that. It's also what Einstein didn't like, but like God doesn't play dice, what he said. So, but I have to admit that I studied the papers of Hooft because I want to know what he's saying and thinking, but I have not followed this line very much. I mean, I do think that eventually he might be right. I don't think that he's going back really to what are called sometimes these hidden variables, but he's doing something similar where he basically says it's not like there's he doesn't like superpositions, for instance. One of the things that I think is very essential in quantum mechanics is that we can have something that sort of, I mean, like a qubit where you have a 0 or a 1, but maybe something in the middle, which we call the superposition. But Hooft doesn't like that, and I feel that there, I think he may be missing something. Anyway, I don't agree with him on this view because I think that quantum mechanics works beautifully. And if you ask me, then the world, that's certainly the assumption I work on, is microscopically really quantum mechanical. And we should sort of use that also in our description.
And so when you think about emergence, I know you were saying we shouldn't only think about it in a reductionist sense. It really is just finding, a deeper description as opposed to a smaller description, so to speak.
Yes.
But do you see emergence as a progression that does hit a rock bottom end at some point? Is there a rock bottom truth from which all the things that we know about emerge, or is this just sort of a sequence of refinements that's asymptotic and just keeps on going?
I like the phrase, it's turtles all the way down. But anyway, so that's the idea that if you ask, I mean, what's underlying the next theory? I mean, one of the things I like about the current language is that this idea of information, there you can really think about what is the most basic form of information, a 0 and a 1. It's very hard to think about anything more tinier than that, or something like that. So we may have that, but I'm not very optimistic that we will really understand everything about the microscopic world. I think this emergence step where we're gonna, derive, say, what we now call gravity and these other forces, may be one of the most fundamental understandings that we can, as humans, can have. But I'm sure that there are more clever beings out there or something out there that have a much better understanding, and there might be some other theory there that I mean, you have to agree that string theory is already one of those enormously complicated things to understand or even work with, that if there's some other more complicated theory that maybe as humans we never would get there, and it might be that such theories exist. So I don't think that we're going to find this final theory. So this dream that we had in the beginning, like this theory of everything, that everything follows from that, I don't think that's manageable for human beings.
But it's interesting for you to describe string theory as complex. Of course, I know what you mean, but wouldn't you say that complexity is emergent? I mean, the starting point of string theory is pretty simple. This basic idea that ingredients are one-dimensional vibrating filaments, and you write down a very simple equation describing them, and then the complexity explodes when you analyze the implications.
I agree. The answer, I mean, but there I do think that we may not have found the final form, first of all, but also the whole framework that we have built eventually. I mean, I'm now having students that want to enter the field, and they have to read a lot of material or study all these books, but they never get to the amount of knowledge that we had in our days when we worked on this. Maybe it's not big important, but I do worry sometimes that what the nice things that we have set up with string theory, if now it's not being sort of actively pursued, may eventually disappear from the knowledge of of the younger people. So I like to train them indeed in learning this, but I do realize it's a big amount of information about science.
No, it's huge.
That they need to, and that's what I wanted to say is that as humans we also have our limits. It's not like we can understand everything, maybe AI will help us a little bit, but I still think it's going to be, I think our best description, I think probably the emergent ones where we say, well, there's something underlying it. We don't know yet what it is. This is sort of how I feel that this thermodynamics is a very good example of that, because thermodynamics is a very general set of rules that apply to many, many things that are underlying it. And you don't need to know what the molecules are made of, what the atoms are made of, but this Boltzmann, who sort of realized that if I assume there are molecules or atoms, I can derive the laws of thermodynamics using what's called statistical physics. And I think there's something similar about deriving the universality of gravity. I mean, I think maybe many systems of a very large class will all lead to the same equations. And I don't need to know which one it is. Because, and maybe we'll never discover. I think that's sort of what I think the power even of emergence is that certain laws are so universal that they will emerge from something very general.
Yeah, I mean, that's a interesting, and to some people beautiful, to some people disturbing possibility, a sort of underdetermination of theory, that there are many different physical realities that ultimately might be describable with exactly the same mathematical equations. And like you're saying, maybe it doesn't matter, because regardless, it yields the same phenomenon on the larger scales that we have direct access to.
Yes. Actually, it's one of the current developments in our field, is people are really saying, well, we don't know which theory it is, so let's just take an ensemble and average over all of them, and then somehow our equations become more simple. I mean, they use basically the same philosophy that the 19th century statistical physicists used now to sort of explain gravity. So I do think but I like that myself. I mean, I think it's more for me gratifying understanding than say there's this one theory that we now know, and because it's only there because of symmetry and so on. I think that idea, which certainly was the one that most people believed in at the time, the early days of string theory, I think is no longer the way I think about it, at least. And also, if I look at how the field is moving, it seems to go more in this direction of this emergence from a very large class of theories that we don't really know yet.
Yeah. Let me just turn to one final topic if you still have enough time, because we're running out of time. But the topic is to do with time, so it all comes together, which is, look, one of the big issues about time is the arrow of time. And that's a question that brings in thermodynamics and entropy. We think about the early universe having low entropy, and then the arrow of time coming from the relentless increase in entropy from the second law. There are people talk about, as we've been talking here, space and time themselves as being emergent. Where do you stand on the insight or explanation for time's arrow?
Very nice question. I mean, in recent years, we've been making a lot of progress by thinking again about entanglement in space-time. And one of the ideas that has come about is that if you only observe a certain part of space-time, then you can forget about the outside. And then you don't have a full, precise quantum mechanical description, but you need something what's called a density matrix, some ensemble average again. It turns out that there you can define, in terms of that for entanglement, an energy, or what we usually call it an Hamiltonian, which describes what time flow does in that region. And so there even time comes from entanglement. So there's a flow direction that's sort of being generated by what's now called the modular Hamiltonian or something like that. But anyway, there's some flow. And I think that what I learned from that is that because it actually sort of like you need this other part that you don't observe. It's so sort of you have this part that you can see and there's things you can't see. And then the time is almost like relative. So the clock goes up here, it goes down there. There's some way in which the direction of time is related to one. In one area it goes up and the other one goes down. So I do like to know what time is if I also want to know what space is. I mean, space and time, as you know, in Einstein's theory are part of the same thing. And if one comes from entanglement, the other one must also come from entanglement. And that sort of seems to work nicely. There's, by the way, a nice language that has appeared from the mathematics that a famous mathematician in the time of quantum mechanics had. It was von Neumann. He actually tried to understand also indeed quantum mechanics in terms of things that we now would call entanglement. And so that also goes about the connection with entropy. So somehow all of these ideas seem to be coming together. And that's one of the more recent developments, is using these, well, the algebras that von Neumann introduced to understand this flow of time and so on. And that actually, by the way, gives us also a way of studying maybe this universe that we live in, like the Sitter space. And, you know, Ed Witten, of course, our famous colleague, has been writing papers exactly about this thing. And so there's also this notion of time. But another thing I like to add is this notion of what's called an observer. He's basically said there must be an observer there, and he has the clock. So maybe time only exists because we are there in the universe to observe it. And it's our time that's sort of determining what the time of the universe is. And I think those get almost to sort of philosophical questions, because, I mean, you really think then we should go back to, well, what's the role of the observer even in thinking about our universe? I mean, we have had many revolutions in our scientific past, like, well, we cannot call ourselves the middle of our universe. We should be, but if you think about the observer, that's the one that's doing the observing in the middle of his universe. I think that's actually a nice picture of even thinking about it. So anyway, I feel that we are making progress, and that we are addressing even these kind of questions about what is space-time made of, but also how does time emerge?
Yeah. Well, look, these are deep and wonderful questions, and it's exciting to hear of the progress that you and your colleagues have been making on the kind of questions, like you said, that do touch upon philosophy. And to me, those are the most exciting questions, when the science actually can begin to inform the philosophical ideas using mathematics and observation and experiments. So, look, it's a very exciting, very fruitful time. And thanks for spending some time with us here describing it. I also just want to say, you know, I've had some of the greatest times when I visited you guys in Amsterdam over the years intermittently. So no doubt I'll find myself there at some point soon. So it'd be great to.
You should come by. And anyway, it's a pleasure to see you again here and to talk to you about this. I enjoyed the conversation a lot, actually. It was
Absolutely
very fun.
great. Thanks for joining us, Erik. We'll talk
Thank
soon.
you.
Bye.
Thank you. Bye.